Welcome to Tevis's milling trim demonstration. So why do customers choose Tevis trim? For improved machine safety, full collision avoidance of the spindle, cutting tools, tool holders and finished part, optimisation of toolpath vectors and tilt directions, template strategy technology for full process standardisation and CAM automation, quick and easy toolpath correction and modification for design changes, auto recognition of standard shapes with conversational output, reverse post-processing for import of historical teach and learn programs, supports both milling trim and laser cutting. Welcome to this demonstration of Tevis's trimming specialist solution. The aim today is to show how the advanced functions and control of Tevis are used to make the process of creating trim programs as easy and intuitive as possible, whilst also showing some high-level functionality and tools. What we can see on screen is our component in blue and our vac fixture underneath it. This data is all held in a layer tree, which allows us to organise all of our data so it's easy to find when we need it in the programming process. The first step in preparing our component will be to split the inner surface away from the solid model. In Tevis, this is a very quick one operation solution, and basically all we do is we tell Tevis to select the inner surfaces, and we're able to pull all of the inner surfaces away in a single component. The advantage of this over other softwares is that other softwares you would have to break the component down into individual surfaces, select those individual surfaces and resave them on a new area. Now the obvious risk with that would be that you can miss areas, you can miss surfaces, you can add extra surfaces that you don't want. Tevis does this automatically so that we get a complete accurate surface in one hit. What that leaves us with is a single sheet surface of the entirety of the inside of the component. The reason for doing this is this allows us to create good clean vectors for the tool to drive its direction along. Once we've created this surface, what we need to do is create some curves. And again, with the curve creation, very simple, very quick process where we simply select the component. So with the curve that we're going to use today, there is always the possibility when the surfaces were generated there's some inconsistencies, and the inconsistencies in the surface will be reflected in the curve. What that means is that any inconsistencies in these curves will interfere with the effectiveness of the toolpath. Now what we want is the truest, most consistent toolpath that we can get, so therefore we need to repair this curve. So a lot of these inconsistencies are generated by the CAD systems themselves, whether it's misalignments, whether it's mistrims, whether it's the laying of the normal surface direction, can all create these inconsistencies. What we're going to do though is we're going to repair this curve. We're going to analyse it and repair it all in one hit, and again we simply select the curve. Tebis is telling me there's 7 errors, so if we zoom in on one of these errors in the little red boxes, what we can see is a mini segment bisecting that line. Now for most softwares what we'd have to do is start by breaking the line, then removing the error, retrimming a new line, and we can't always guarantee consistency with the original curve or perfect alignment with the original surfaces. What Tevis will do is it will heal it while still maintaining the tolerances and accuracy of the curve against the surface. What this means is that the curve is now 100% consistent, but also just as accurate as it was before. Okay, so now that we've done the preparation work, we need to look at programming. So with Tevis, what I've done is I've created a template. So this template is set up around the Belotti machine. What this means is that we can have Tevis automatically select data and also predefine data to make the programming process as consistent and as quick as possible. So in this particular template, the finished part and clamping devices are going to draw the data directly from the layer tree. So the finished part will look automatically at the part layer, and the clamping device will look automatically at the clamping device layer when it's instigating its collision checking. What this means is that it doesn't matter what part that we load up and what part we apply this template to, Tevis will automatically update itself and take into account the new component. When we come to the programming process, the actual programming operation, I've pre-selected a tool What I've also done is I've pre-selected some of the parameters and things like lead in and lead out. And what this allows us to do is, again, to create very quick, very consistent programs. If we have a quick look at our tooling, we select tooling from an external library. What this means is the library is held either on a server or on the cloud. And what this means is that no matter how many people are working within your company, if they're working on Tebis, they have access to the same tool library as everyone else. This creates absolute consistency in tool selection and in tool process. So along with a full form tool, so these tools are constructed exactly the way the tools are in real life, we also maintain a cutting library. So what this means is that Tebis is able to cross-reference the machine that we're working on, the material that we're using, the cutter that we're cutting with, and the type of machining process to create the absolute perfect cutting conditions. So what we can see on screen now is our cutting conditions, where Tebis is able to cross-reference the tool, the machine, the operation and the material. We can also include things like step down and step over for multi-step cuts and for general milling, and we can also incorporate cooling conditions. But in this instance, what we're going to do is we're going to select the curve geometry and we're going to set the component geometry. So the curve geometry will give our tool a direction to cut, and the surface geometry will give us a normal direction for the tool. Now, as we can see on screen, we have our cut curve. We have these yellow lines, they're the vectors. These will denote the direction of tool. We can also see the side of the curve that we're working on and the direction of cut. Now, in the first instance, what Tevis will do is actually produce a pretty good contour. Now, whilst there might be some inaccuracies in it through calculation, this will actually produce a perfectly serviceable and a perfectly accurate toolpath. What we might want to do, and what we're going to do, is tidy this up. So as we went around some of these corners, we had some excess head movement, we had some excess rotation in this area here. So what we're going to do is we tidy this up and make this the most accurate and the most efficient that it can be. So we're on to vector manipulation. When we come to working with vectors in Tebis, these yellow lines are the vectors. This will denote tool direction. Now, a combination of tool direction and head angle tells Tebis exactly where the tool is at all times. Now, when we come to start moving the head around in Tebis, we have a number of options. We are able to simply grab the head and move it to where we want it. Now, this allows us to create some approximate positions. It allows us to visually avoid things like clamps or secondary fixturing. What we would generally do though is, as you will have noticed, as we manipulate these angles, on the right hand side the numbers are changing. What this means is we've got the opportunity to estimate where we are and then nominalise the values if we want to. So in this instance, at the start of the program, I'm going to start at 90 and 0. So along with being able to manually move the head on screen, being able to manually input values into the angles, for safety reasons, we're also able to toggle the head. What this means is we can flip this head position around. Now this is unique to Tebis. Every other software is unable to track the head position. For most other softwares, this head position is not specifically designated within the CAD. We can control the angles, but we don't know exactly where this head is. In Tebis, however, what you see on screen is exactly what you get. If this head position is here, then that is where the head position is. What this means is that we have the ability to control the head position. That way we know exactly where the head is at all times. What this means is that we shouldn't be able to collide with another component, we shouldn't be able to collide with any ancillary fixturing, and it makes the safest programs possible. So the next thing we're going to do is start to tidy this program up, and what we're going to do is we're going to use vector manipulation. The basic process for this will be to create control points on the curve, and then with the control points we can control where Tebis has the head. Then what we do is we go back and we control how Tebis treats the curves in between. So in this instance I'm going to nominalise this value to 90 by 0 and create a set point. What I do then is, or what we have then is, start of the curve is 90 by 0, end of the curve is 90 by 0, but we still have movement on the curve. What we do though is we'll tell Tevis to stay straight to the vectors. What that gives us is the starting point, the curve and the end point are all at 90 by 0 all the way through. What we'll do is we'll continue to break the curve down into large chunks like this and use these controls to get the best possible toolpath we can. So if we come to this area here, and again, I'm going to nominalize these values and create a set point. So now we have the head vertical. We're then going to tell this to rotationally align. So what we have now is a toolpath that goes from dead horizontal and rotates smoothly and cleanly towards point 3. The next area to isolate will be this large straight area. So what we're going to do is create another control point. And again, tell Tevis how to behave in between. So as you can see, what we're doing is we're building up the movement into strategic chunks and controlling the head at every point in the process. Now what we see in this area is what looks like a very misaligned vector. What's actually happened is, as Tevis has stayed normal to the surface and rolled around these curves, the head is tilted to compensate for it. What we're going to do though is straighten this vector up to align with the rest of them to give us a nice clean head movement. So the process is exactly the same as before. Create a control point, then tell Tevis to stay straight. What we can see there, movement is very much smooth, the vectors are all in alignment now, and what we get is a nice move around this curve. So as we feed the tool through, we can see very clean, very nice movement through there. Now with this heavily rotational area, what we want to do is allow Tevis to do a little bit more of it itself. So what we're going to do is allow it a little bit more freedom, a little bit more movement. But we're going to nominalize the value at the end. And in between, we're going to tell Tevis to rotationally interpolate. So what this means is when we come from point 5, Tevis will very cleanly and very smoothly roll around that component to create a nice toolpath. Now with these last couple of areas, we're going to do exactly the same process. So we have the nominalization and set point. We're going to straighten the vectors, then come to our exit point, nominalize, again, and straighten those vectors as well. So what we have is a very nice clean smooth movement all the way around there now. What that should give us in total is a very nice, very clean toolpath for the sake of about 3 minutes work. So as I play this through now, what you'll see is that we've eliminated the excess movement, the excess rotation to create a very clean, very effective toolpath. So along with this type of manipulation and this alignment of vectors, what we're able to do is we can modify this curve as we go along as well. We've all had a situation where designers have made a change or we found a fit problem, and what we need to do is modify this curve. What we don't want to do is have to come out of the toolpath, create new geometry, go back into the toolpath and reprogram the whole thing again. What Tevis allows us to do with path correction is to add the curve that we want to change. So now we have this extra curve area here, and we can simply add this into the process. And what we get is a situation where Tevis now modifies the curve, but still applies the same cutting parameters. So as we come to the end of the toolpath there, if we hit the play button from here, what we'll see is instead of going around the bottom edge, we're now going through the modified curve to create the new form that we need. Very handy for on-the-fly adjustments. Also, it negates the need to interfere with the toolpath that you've already got. One of the problems a lot of trimmers come across, especially with thin sheet plastics, is when we're machining around corners, we can sometimes get some snatching and breakage on these absolute corners, whether that's through a combination of the cutter dynamic or whether it's the clamping. The ideal way to deal with this is to create some relief in the corner. So if we come back to our programming process, we can simply add some corner movement. And what we have now is the toolpath hasn't been interfered with, so you can still see our perfectly aligned vectors and nice smooth movement. But what's happened now is the tool comes to the end of the cut, comes out of the material, disengages completely, rolls around and then re-engages in a clean smooth movement. This eliminates the chance of this corner snatching, creating a poor surface finish or indeed breaking it off completely. So that's contour machining in Tevis with vector manipulation. What we've done is we've done the preparation of the component, we've created the curve, we've smoothed and made the curve more efficient. We've then added a modified curve into there, all in the space of a few minutes. The next thing to look at will be to have a look at 2.5D geometry. So when we're talking about 2.5D geometry, we're talking about circles and squares and more base type features. So in this case, we're just going to change the program. All the parameters are kept the same, but what we're going to do is just select the circle. So within this circle now, what we can see is that Tevis has automatically recognised that it's a circle and tried to apply 2.5D geometry to it. What we're going to do quickly first is just change it to a contour. The reason for this is just to demonstrate how a contour behaves versus a 2.5D geometry. So this contour now will follow the curve that it's told to, which is the circle, but what it will also do is try and align the tool with the surface, giving us 5-axis movement. Now for a feature as simple as a circle, we don't really want the 5-axis movement. What we want is to go in and just create a circle in 3+2. So what we do is, if we tell it it's a circle, Tevis now applies 2.5D geometry. It's now not looking for the surface normal, it's just applying the geometry as it sees on screen. So what we get now is a more consistent movement without the rotations. The big advantage of this is it should be much quicker, it should be much more efficient, and should also be more accurate. Machining with the head locked and in position is always going to be more accurate than using 5-axis movement. So, some of the other advantages of 2.5D. We don't have to treat this circle as a circle. So one of the common changes that we'll make will be to change a circle to a slot. And we can do this just to aid in finish and fit, to aid in the assembly process later on. So what we can do is we can change it to a slot, and then we can go and adjust the slot and make adjustments to suit the component. What we find quite a lot in trimming is that there's a fair amount of shrinkage, a fair amount of distortion and general variation in manufacturing process. We're not limited to slots. We can also create squares, triangles, hexagons, and what they will do is Tevis will apply the 3D geometry, the 2.5D geometry, sorry, but using the circle parameters. If we come back to a circle, we also have another level of adjustment in that we can use path correction. So if we change this back to a slot, we can also have a look at the next level of path correction, which is available to 2.5D features. So what we have is geometry adjustment. So we can actually change the length of the slot to 20mm. Without changing the geometry underneath it. This is excellent for on-the-fly adjustment or for modifications to programs where you don't have the time to wait for a new model or wait for design approval. It's something that we can just get on with and something that we can just make happen within Tevis. So we can change the width. But not only that, if we're still having problems with positioning, we are also able to adjust positioning of the component or the feature within the component as well, and this includes rotation. So between being able to change the type of shape, being able to change the size of the shape, but also being able to change the position, it means we're almost guaranteed to get finish of fit every time. So that's Tevis trimming in a nutshell. We've had a look at preparing the component using some of our internal tools. We've also created the geometry that we needed to manufacture the part. We've also programmed the part, including vector manipulation, to give us a good, clean, smooth toolpath. We've modified the toolpath, and we've also worked with some 2D geometry. What we can also do with Tevis is to create fixturing. Now, rather than take the time and expense of creating full form vac fixturing, what a lot of our customers will do will create an interlocking fixture to create one-offs and fast turnaround work. So what we're able to do is, again, choose the inner surface of the component, choose what thickness our material we're making the fixture out of, and the base plate. And what Tevis will do is automatically create a fixture that we will be able to manufacture this trimmed component on. So as we go through here, we can add extra stanchions, we can move stanchions around, and basically just modify this just to suit exactly what you want. If we go to the next area now, Tevis will create some thickness to these stanchions, or calculate the thickness for the stanchions. And then what will happen is we should get the startings of our stanchion formation. As you can see, we have numbers on each of the stanchions on the base plate so that we know how to assemble the fixture. But what we're also able to do is to create some clearance and some weight reduction on these stanchions. A lot of our customers make these out of plywood or MDF, in which case the more weight reduction you can add to it, the better, because these fixtures can get awfully heavy. Then what we get is a basic layout. This will allow us to lay a sheet of MDF in the machine and basically just cut the fixture out, ready for manufacturing. The next operation then will flesh the fixture and give us a full 3D version of the fixture, which allows us to use this in the programming process. So as an alternative to the full form fixture that we saw with programming with, we can actually use this lattice fixture instead. So, Tevis trimming. Fast, concise, accurate, and above all, safe. Hopefully you've seen that all of these processes are very easy to use, very easy to apply, and that they are very effective and very simple. So in summary, for milling, trim and laser cutting, we have improved machine safety, full collision avoidance of the spindle, cutting tools, tool holders and finished part, optimisation of toolpaths, vectors and tilt directions, template strategy technology for full process standardisation and CAM automation, quick and easy toolpath correction and modification for design changes, auto recognition of standard shapes with conversational output, reverse post-processing for import of historical teach and learn programs, and supports both milling, trim, laser cutting.